Hi. In today's class, we're going to strengthen our ties between the periodic table and the extended Bohr model. Let's start with the periodic table. The elements in the periodic table can be classified by whether in the S, P, D, or F block. And within each block, the row is controlled by the principal quantum number, 2p for the top row, then in the p block, 3p, 4p, the principal quantum number, the n value, is increasing, going down. As we make our connection to the extended Bohr model, we're going to pay particular attention to the S and P block. So if we take out the D and F block of the periodic table reduces to the rectangle as shown here. And going down, the principal quantum number is increasing. So let's see how this connects to the extended Bohr model. The extended Bohr model has two equations, two proportionality relations that are most important. R is proportional to n squared over z effective, and the total energy is proportional to z effective squared over n squared. The big change from the Bohr model is that z has been replaced by z effective. Okay. We are connecting to the periodic table. We're connecting to real elements. We're going to start making measurements on the elements themselves and how do measurements compare to R and E total. The atom size is a measure of R. When an atom is big, the R of the atom is big. Energy can be measured two different ways. The first way we can measure energy is by the ionization energy, which is abbreviated IE. And you start with an atom, and you are going to look at a minimum energy. So the ionization energy is a minimum energy. And the atom will absorb the minimum energy of light so that the atom will eject an electron. A free electron comes out. So the electron goes up in energy, the atom from absorbing the photon, and the atom, having lost an electron, becomes plus charged. But there's a second way we can measure energy, and that's called the electron affinity. Abbreviated EA. And EA is where you start with an atom and it encounters a free electron. And the EA is also a minimum energy. The free electron gets absorbed by the atom, and when it gets absorbed by the atom now becomes negatively charged, and the free electron has gone down in energy. And what's the minimum energy of light that can be released? So now that we know what kind of measurements we can make, we can look at questions about size and ET. And we have, again in the extended Bohr model, R, which is a measure of the size, is proportional to n squared over z effective, and ET is proportional in the extended Bohr model to z effective squared over n squared. And so the question is, here's our periodic table. how do N and Z effective change going left to right or top to bottom? So going left to right, the N value is constant. In each row, it's all 2p or all 3p and so forth. So take the top row, it's 2s and 2p. The N value is not changing. The only thing that's changing is Z effective. And from imperfect shielding, Z effective gets larger as we go to the right. By contrast, when we go down, N is always increasing. The first row in that table is the 2s, then N equals 3 and 4. Z effective is changing, but the dominant effect going down is N. And N increases as we go from the two principal compound number 2 to 3, and so forth. And so now we can start seeing answers to our questions. Let's look at size. So size is proportional to N squared over Z effective. Going to the right, Z effective is in the denominator. Z effective is getting larger, and if Z effective is getting larger, R, since Z effective is the denominator, is getting smaller. And similarly, we can go down. Going down, N is dominant. N is in the numerator here. Therefore, R is getting bigger. And we can look in the same way at the energy. In the energy going to the right, again, it is Z effective is getting larger, but now Z effective is in the numerator, and therefore the magnitude of the total energy is getting bigger. Similarly, going down in the periodic table, the N value is the dominant factor. N now is in the denominator. As N gets bigger, the magnitude of the total energy gets smaller. And we can see that here. So size, atoms are getting smaller going to the right due to the Z effective effect of imperfect shielding, and size going down in the periodic table, atoms are getting larger because N dominates. For the magnitude of the total energy, due to the imperfect shielding going to the right, Z effective is getting bigger, total energy is getting bigger, and going down as N increases, the magnitude of the total energy decreases, gets smaller. But remember that energies in atoms, of electrons in atoms, are below the ET equals 0 value. They are negative numbers. So when we say larger, we mean it's more negative. It's a larger negative number. And when we say smaller for the magnitude of total energy, we mean a less negative number. And we'll practice this in class.